Welcome back, everyone. In this section, we've already discussed the similarities between the algebra of real numbers and the algebra of matrices. We're going to step further and develop the algebra of matrices to include the solutions of matrix equations involving matrix multiplication. So let's begin with the equation ax plus b, provided that a cannot be equal to 0. And we're going to solve for x. My bad. It's ax equals b. There we go. So to solve for x, we can simply multiply both sides by a to the negative first power. And as a result, the a's on the left side cancel out. And instead it becomes 1 times x equal to a to the negative first power times b. And as a result, x is equal to a to the negative first power times b. Redundant, yes, but there's a reason for that. So this value right here is what's known as the multiplicative inverse. And it's the multiplicative inverse of a, because what happens when we multiply a to the negative first power times a? It simply becomes 1, which is the identity element for multiplication. The definition of the multiplicative inverse of matrix is similar. So, because we're covering the inverse of a matrix, let's introduce ourselves to what it means for a matrix to be invertible or non-singular. So let's say we have the matrix A, and there exists an n by n matrix of B, such that A times B is equal to B times A, which is equal to I sub n, which is our identity matrix of the order n. What is matrix B? Well, in this setup, matrix B is the multiplicative inverse of A. And any matrix that doesn't have an inverse is non-invertible or singular. It's also worth noting that non-square matrices do not have inverses. And what I mean by that is, if matrix B is an m by n matrix, and m does not equal n, what ends up happening is that B ends up not having an inverse. It's also worth noting that while non-square matrices do not have inverses, it's not always the case that square matrices do have inverses, and we're going to cover that in one example. So in this first example, we're given two matrices, A and B. And we have to show that B is the inverse of A, and by doing so, we're going to use the equation AB is equal to the identity matrix, which is equal to the other way around. And this can be proven numerically quite easily too. So AB, what does that mean? It means you're multiplying two matrices. And what do we call a matrix with a diagonal of 1s with the rest of the coefficients being 0s? And if you remember and recall that it's an identity matrix, then you are correct. Hopefully you guys still remember how to perform matrix multiplication. And You will see that I'm going a little bit out of order because if you plug this into your calculator, you would get that regardless of whether or not it's A times B or B times A, you are going to get these two matrices. And as a result, we have proven that AB is equal to BA, which also equals the identity matrix. Now what happens when we're given one matrix and we're supposed to find the inverse of that same matrix? What do we do? Okay, recall the equation AX equal to I. Let's define each variable. A is our coefficient matrix, and we know I as our identity matrix. What exactly is X? Well, in this context, X will be the key to finding the inverse of this matrix. If we multiply both sides by a to the negative first power, like what we did earlier, we end up getting the value of X, and therefore we get the coefficient that gives us the product leading to the identity matrix. Hopefully that made sense. So let's plug in what we got. 1, 4, negative 1, negative 3 times x11, x12, and we have x21 and x22. Times the identity matrix, and equating corresponding entries, we obtain two systems of linear equations. Can you guess what those are? Go ahead. Remember, if you are still wondering what the two systems of linear equations are, here it is. So we have x11 plus 4x21, and then we have x12 plus 4x22, and then we have negative x11 minus 3x21, and we have negative x12 minus 3x22. These values are from performing matrix multiplication for the matrices A times X. And of course, this all still equates to our identity matrix. So solving the first system, we can deduce that x sub of 1 is equal to negative 3, and x of 2 is equal to 1. And when we solve for the second system, we find that x12 is equal to negative 4, and x22 is equal to 1. As a result, the inverse of A is equal to X is equal to a to the negative first power, which is equal to negative 3, 1, negative 4, and 1. We can use matrix multiplication to check the result. And by doing so, we refer back to this equation. AX equal to I, and we have the matrix 1, negative 1, 4, negative 3 times our new X variable, and we can check from there. Now, if you're still confused, don't worry. We're going to go back a little bit. If you guys understood it the first time around, go ahead and skip forward. But for those who didn't get it, let's go back a bit for you guys. So we have these two, we have our systems of equations right over here. And what happened was that we were able to solve for the x variables. Well, we were able to solve the x variables in the simplest way possible, because in the first column, the x11s cancel out, and we get x21. And if we go to our identity matrix and correspond it to the first column of the identity matrix, we get that x21 is equal to 1. And if we apply, if we look for x of negative, oh my god. Okay, so let's say we've been forsaken with this 3x3 matrix, and to make things harder, we've been tasked to find the inverse of the same matrix. So to start, we're going to do something contemporary, and we're going to join the identity matrix to A. What that means is, well, by joining two matrices, we use this notation, and it's simply the coefficient A adjoined to our identity matrix, I sub n. Can we guess what n is supposed to be? It's not 1, and it's not 2. Sure as hell isn't 0. But if you said it was 3, you are correct. And now, let's use elementary row operations to obtain the form of this adjoint matrix. So what that means is we gotta move the identity matrix to this side, and using Gaussian elimination, we gotta using Gaussian elimination, we gotta move A to the other side. Sweet. And then we're gonna grab this matrix and perform our elementary row operations. Okay. So let's see here. What do we do first? Well, for starters, we can add. What if we add row 2 to -1 times row 1 and move it to row 2? Let's just start with that. So, we have row 2. We have row 2, and we're added to -1 times row 1, and we're gonna move that to row 2. As a result, we get a change in row 2, and rows 1 and 3 will be the same. Alright, row 2 is going to be 0, 1, -1, -1, 1, 0. Okay. And then we're going to grab row 3 and multiply it to 6 times row 1 and move the change to row 3. And as a result, we should get a change in row 3 with rows 1 and 2 being the same. I'm going to duplicate the first 2 rows. And let's see here. -6 plus 6, 0, -4, 3, 6, 0, 1. Okay, and then we're going to grab the third row again. And we're going to grab row 2 and multiply it by 4. And bring the change to row 3. As you can see, we're brutalizing row 3 here. So this implies that rows 1 and 2 will be the same. And we'll just concentrate on thinking to row 3. This becomes 0, 0, -1, 2, 4, and 1. Okay. Now we're going to grab row 3 again. And this time we're going to multiply by -1. And where are we going to bring that row? You guessed it, row 3. And let's see here. Okay. Once again, rows 1 and 2 remain the same. And we're just multiplying third row by -1. So that's 0, 0, 1, -2, -4, and -1. Sweet. Now let's add row 2 to row 3 and bring that change to row 2. Oh look, we're done engaging row 3 for now. Therefore, rows 1 and 3 should be the same. And we can concentrate our thinking to row 2. So we are left with 0, 1, 0, and -3, -3, and -1. Okay. And the next step will be our last elementary matrix operation, where we just add rows 1 and 2 and move the difference or sum to row 1. Therefore, rows 2 and 3 are the same, and row 1 should be altered. So we get 1, 0, 0, -2, -3, and -1. And this is the same as I times A to -1st power. So the matrix A has an inverse, and its inverse is, well, to the right of the identity matrix. And yeah, that's pretty much it. As you can see, this method is very tedious. It's pretty lame, and this is why you should really invest in a graphing utility, because honestly this stuff blows really bad. So remember when I said that not all square matrices have an inverse? Why is that? Well, in this example we're about to find out. So let's say we're given the same D/3 matrix, and let's also say that we were to join it to the identity matrix. So we get the following matrix right here. And I'm not gonna do the whole Gaussian process like we did before. I would just put it in your graphing utility or some online calculator, because this is what we end up having if we were to apply Gauss-Jordan elimination. We end up getting these following columns. And notice over here we have a row of zeros. This is an indicator that it's not possible to rewrite the adjoint matrix of the coefficient matrix and identity matrix in the form of the identity matrix to the inverse. Visually, it means that this adjoint matrix cannot be this adjoint matrix. This means that there is no inverse, or it is singular. Now let's say you're sick and tired of Gauss-Jordan elimination, and you value your time way too much to be doing this. Okay, I understand. Let's say we have a matrix of A, B, C, and D. And in this context, A isn't supposed to be invertible, and as a result, it's only invertible if AD minus BC does not equal 0. And yeah, that's pretty much it. Now, what this means is the inverse of A is 1 over AD minus BC times D negative B negative C and A. So the denominator right here, this is our determinant. Make sure you remember that word, it's gonna come to us later. And it originated from multiplying AD and AB. We multiply AD and then we subtract the product of B and C. Hence the denominator. And that's pretty much it. If it equals 0, there is no inverse, and that is one shortcut you can apply. A quick disclaimer, this only applies to square matrices. And if you have to find the inverse of a non-square matrix, what does that mean? Well, we've already established that non-square matrices are singular, so that shouldn't have even been a question. Okay, so we're going to do an example that requires employing determinants. So we're given two matrices, two 2x2s, and we're going to find the inverse of each matrix using determinants. So for determinant of A, and by the way, determinants can be denoted as det of the matrix. So anyways, to find the determinant of A, to find a determinant of A, we simply grab 3 times 2 minus negative 2 times 2. And let's see here. Hold on. It's actually negative 2 times negative 1. Let's work the math out. 6 minus 2, that's 4. This means something. Can you guys tell me what it is? What happens when the determinant of matrix does not equal 0? And if you said that it's an indicator that the matrix has an inverse, you are correct. So we can now form the inverse by interchanging the entries in the main diagonal, changing the signs of the other two entries, and multiplying by a scalar of a fourth. This means a to the negative first power is 1/4 times 2 to 1, 3, which is a half in the first column, a quarter, and 3/4. Was that too fast for you guys? I don't blame you if that was. So this matrix right here, it comes from this rule right here, where it is 1 over the determinant times the matrix with the first column being D and negative B, and the second column being negative C and A. And then we applied that to this matrix and multiplied or distributed the scalar accordingly. Now, what would the determinant of B, matrix B, become? So for B, we have 3 times 2 minus -1 times -6, and what does this mean? N equals 0. Figure that out. What does it mean? Well, unlike matrix A, the determinant is 0, and when the determinant is equal to 0, that means there is no inverse. And there you have it. We have found the inverse if possible for the 2 given matrices. Now let's touch base and talk about the properties. So let's say A is a matrix with an inverse, and K is a positive integer, and C is a non-zero scalar. What if we have A to the negative first power to the negative first power? Well, it turns out it actually equals A. Don't believe me? Plug into your calculator where A is any real number. Alright. Okay, so let's say we have A is raised to a positive integer K, and the whole quantity is to the negative first power. It turns out we just have A to the negative first power times A to the negative first power, and so on, depending on what that value K is. And as a result, the series, it ends up being our K factors. Now, what if we have a scalar times our matrix to the negative first power? Turns out we can distribute the exponent, which is 1 over C, times the inverse of A. Alright. Now for the fourth property, what if we have the transpose of A to the negative first power? What would that look like? It turns out that it's simply A to the negative first power transpose. So it looks like the exponents just switch out. And there you have it. We have uncovered the properties of inverse matrices. Okay, in this example, we are tasked with finding the inverse of the square of a matrix. So we're often tasked with A to the negative first power, this times A to the negative second power. How many ways are there to solve this problem? It's a lot. It's more than one actually. It's 2. So the first way is we're going to square the matrix A. And that is simply just the matrix times itself, which is just this matrix times this matrix. We can then apply basic matrix multiplication, and we get 310 in the first column and 518 in the second column. We will then be able to determine whether or not this matrix even has an inverse. Do we remember the quickest way to find that out? And if you recall, it's using the determinant. So 3 times 18, that is 54, and that 54 minus 5 times 10, that's 50, and that's 4. What happens when the determinant doesn't equal 0? No, it's not linearly independent. We'll get to that later. It's just any non-zero determinant will confirm that a given matrix has an inverse. So we have a squared. Let's take the inverse of that. And we already have the determinant and the matrix. What happens to the matrix? So if you said 3 and 18 switch places and 5 and negative 10 are both multiplied by negative 1, you are correct. Ding ding ding. And we just distribute the scalar, and it becomes 9 halves in the first column, negative 5 halves, and then the second column is negative 5 fourths and 3 fourths. And there you have it. That's one way to find a to the negative second power, or the inverse of the square of a matrix. Another way is like this. So let's look at A and find the determinant of it. So we have 4 minus 2, so that's 2. Therefore the fraction is going to be 1/2. And A and D switch places. B and C both multiply by negative 1. And then we just distribute the scalar, and we get 2, negative 1, negative 1/2, and 1. We can then grab a to the negative first power and square it. And as a result, it is simply this matrix times that matrix. You can plug it into a graphing calculator or solve it by yourself, but what ends up happening is you get the exact same answer. So both methods produce the same result, and that is how you find the inverse of a square matrix. Okay, so we have found the inverse of a square matrix. Can we find the inverse of a matrix product? And it turns out we can. So we can use a determinant, but that only be half the battle, because since it's a 3x3, the matrix, you can't just switch A and B and multiply C and B by negative 1. No, it doesn't work that way anymore. So we're going to start off to find AB quantity to the negative first power. We will have to apply Gaussian elimination, and we respect ourselves too much to manually do it. So I'm running this to my graphing calculator, and you should get this result. And we do the same thing for B with our graphing calculator. And then we have the inverses of our two given matrices, and it's just a matter of it is just a matter of this matrix multiplication. So this expression ends up being b to the negative first power times a to the negative first power. And as a result, we get to multiply this matrix by this matrix. And then we run that into a graphing calculator, and we get 8, negative 8, 5, negative 5, 4, negative 2, negative 2, 3, and negative 7/3. And there you have it. We have found the inverse of a matrix product. And we did that by finding the inverse of the two given matrices. And it was just a matter of matrix multiplication in the end. Okay, so we went over finding the inverse of a square matrix and finding the inverse of the one before that, whatever that was. Oh yeah, it's a matrix product. But now we are tasked with finding an inverse matrix, but we were given systems of equations. It may look menacing, but the coefficient matrix for each system in A, they're the same. It's simply just 2, 3, 2 in the first column, 3, 3, 4 in the second column, and one column of ones. Plug that into your graphing utility to find the inverse, and we get negative 1, negative 1, 6, 1, 0, negative 2, 0, 1, negative 3, and boom. That is our inverse using Gaussian elimination, or if you're smart, plug it into your graphing utility. Okay. Now, let's recall the equation ax is equal to b. And when we were solving for x wound up being a to the negative first power times b. And let's look over our systems of equations. We have we have our inverse matrix is, we solved for that. What exactly is b? Well, it turns out, you guys, that b ended up being the other side of the equation. These values right here, they are our b values, and because we're solving for x, everything's already given. Therefore, for the first matrix, it is simply the inverse times the column vector of 1, 1, negative 2. This is supposed to be negative 1. Negative 1, 1, negative 2. And in doing so, it produces, it all equals to x. And when you apply matrix multiplication, you get 2, negative 1, and negative 2. What does this mean exactly? Well, it simply means that x is equal to 2, y is equal to negative 1, and z is equal to negative 2. And now, we rinse and repeat, but with a different b value. So we grab this matrix and multiply by the column vector of 4, 8, and 5. By applying matrix multiplication on your graphing utility, we get a column vector of 4, 1, -7. In this system of equations, different solutions are produced where x is 4, y is 1, and z is -7. Now for c, yes, we still have the same inverse, but we have a column vector of 0. Therefore, what does this mean exactly? What are we going to get as an answer? And yes, you are correct to assert that you get a column vector of 0. What does this mean? It simply means the solution is trivial. When you get a column vector or a row of zeros, or a solution of zeros, its solution is trivial.